Good morning again. Let us start. Is the presentation visible?
Yes, sir.
Okay. Okay. So we have been discussing about testing strategies. We discussed about the black box testing, particularly equivalence class partitioning and boundary value analysis for designing test cases. And then we have been discussing what is a wider range of testing often are required in terms of white box testing. And we saw that both of them are actually needed. White box testing, as we have observed, is based either on we are checking coverage of different program elements, or we may be checking for specific faults. They could be targeted, directed tests for specific faults. So in terms of coverage, we have seen, I can show you the summary slide. We have seen these kind of tests, that is statement coverage, then condition coverage or decision coverage, the branch coverage we have talked of, the condition coverage, and the modified condition or decision coverage, by which you can significantly reduce the number of test cases for analysis. So, and we have also talked about function coverage. We saw the LCOV report and so on. So these are some of the more commonly used techniques for coverage. They are very powerful and kind of comes as a standard for code check-in in almost every software company. We will now get into talking about some more methods, some more powerful methods of coverage, and which will need certain kind of program analysis to be done. So the next what we talk about is known as path coverage. The path coverage, basically, what if you see what we have done in terms of coverage so far, we are checking for specific elements in isolation, like either it is statements in isolation or function in isolation, or we are checking for branches, or we are checking for conditions, or so all these different elements, program elements, are independently being tested and checked for coverage, that did I have at least one test case which checked that program element. So these coverages really do not take into consideration the control flow through the program. So path coverage is focused primarily on that. What I intend to do specifically is we intend to really cover all the paths in the program. A path in a program is a flow of the control from the beginning till the end, the start of the program till the end of the program. So could I try to test for all the paths in the program? Now, naturally, if I look at all the paths in the program, then it is an infinite set. With loops or recursion, it is an infinite set. Even if I consider the flow through a loop for a given set of iterations, even then it is an extremely large number. So for path coverage, we introduce a new concept of linearly independent paths. So again, we are trying to identify paths which are kind of representative for that program, so that checking them is a strong indication for checking all paths. So this is defined in terms of what is known as a control flow graph, or CFG. So we need to first construct a CFG, the control flow graph, the sequence in which different instructions of a program get executed, and then analyze that graph to see the way the control flows through that program. Now, CFG can be constructed in, again, at multiple levels of abstraction. And depending on, for example, I can have a CFG, which is simply a function call graph. Just see which function, I mean, everything starts with main, let's say. So main calls function F calls function G, then G returns, F again calls function H. So I can just, in terms of function calls, I can form a graph of which function is calling which one. That is called a call graph. But CFG is usually done at a lower level of abstraction. It is typically done in terms of statements of a program. And when you will do compiler course, you will see that CFG will be done at an even lower primitive instruction level. We will define something like 3 address code, and we will do CFGs in terms of the 3 address code and so on, the basic blocks and so on. But that's later. Right now, the abstraction level we are focusing on are statements. So we number all the statements in the program, and as the control flows from one statement to the other, we represent the statement by note and draw an edge to show this control flow. So that's the basic idea. An example will make it clearer. So think about this, consider this program, right? This is finding GCD by Euler's method, you know. So we have numbered each and every line of this program, right? I've left out this function line, the first line, because we are not showing the context in which this function is called. So obviously, when we are doing the analysis, it is obvious that everything starts with that function being called. So we number the statements like this, and then we have 1, 2, 3, 4, 5, 6. 6 different nodes we draw, right? 1, 2, 6. They represent the statements. And then we try to see how the control can flow. So if I say statement 1, which is a while loop, so here is a condition check, x not equal to y. So there are 2 possibilities. One is x is actually not equal to y. If x is not equal to y, the control will flow to 2. So I have this edge showing this control flows to 2. Or if x is actually equal to y, then this condition fails, and I get out of the while loop to the immediately next statement, which is the return statement. So I have an edge from 1 to 6. So this is the edge that shows. Again, at 2, I have 2 possibilities. X greater than y, I go to 3, the left edge. Or x is not greater than 3, not greater than y. So I go to statement 4, which is here. Now, after doing, depending on whether this is true or false, I do either the then part or the else part. But after that, the control always comes to this statement 5, which is the end of scope for the while loop. So x greater than y, I go to 3, and after that I jump over 4 and come to 5. So from 3 I come to 5. Again, from 4 also I come to 5. So this is, so 2 kind of is a forking node, and 5 kind of is a joining node. And what does it do? The control goes back from 5 to check the condition again. So I have a edge from 5 to 1. Right? So once you have done this, now it is a for a small program, doing this by hand is not difficult. But when you have a large program, then doing it by hand would be really difficult. But certainly there are tools like compiler itself internally has to do this to be able to do different analysis on the program. So once we have the control flow graph, we define a path through a program, which is the start node here, not separately demarcated. You can put an in arrow here to show this, because you can see that this looks like a finite state machine. So this is the start node, and this is the end node, right? Terminal node. So any path starts from the start node, follows the edge sequences, and reaches the terminal node is called a path. So 1 to 6 is a path. 1 to 2 to 3 to 5 to 1 to 6 is a path. But 2 to 5 is not considered a path. 2, 4, 5 is not considered a path. Or 1 to 3 is not considered a path, and so on. So of these paths that I can have paths like this: 1, 2, 3, 5, back to 1, 2, 4, 5, back to 1, 2, 3, 5, back to 1, 6. This is a path, right? So we define linearly independent path if it includes at least one edge from the other paths, one edge that is not included in other paths. So rather more in a more specific way, a linearly independent path is one which you cannot build by using other linearly independent paths. For example, here you have three linearly independent paths. One is 1 to 6. One is 1, 2, 3, 5, back to 1, 6. This one, second one. And one is 1, 2, 4, 5, back to 1, 6, the third one. These are the only three linearly independent paths. For example, if I do 1, 2, 3, 5, back to 1, 1, 2, 4, 5, back to 1, 6, then you can see that that path can be constructed from combining one or more of these three independent paths. Right? So this is the linear, this is called what is a linearly independent path, which is, again, for a simple program, it is easy to see and construct. But for a complicated program, you will need an analysis tool and some smart graph algorithms to be able to do that. So those solutions exist. So what we focus for path coverage are covering these linearly independent paths. That is, we want to provide enough test case so that at least all of these linearly independent paths get tested. Right? Here is another example of linearly independent path. This function, this is in Java, right? So this function is trying to check if a number is prime. So I start with 2. I keep on. This is a very native program, right? So I start with 2, and I keep on going up to n-1, which actually is not required, but this program is just trying to do that. And I check whether I divides n. If it does, I return false. It cannot be prime. But if the loop completes without returning from here, then I return true. Right? So I have marked the statements here, making it little simpler, not demarcating the end of scope for if or the end of scope for while. We will directly make the jump. So we have 6 statements: A, B, C, D, E, F, A, B, C, D, E, F. So we enter into A, then we go to the beginning of the while loop condition B, and there are 2 possibilities. One is I could go to C, which is checking this if condition, or this condition could fail and I go directly to F, to the return. At C, again, I have 2 possibilities. I can either go to the next statement, which is return false, or I can go to E, which is incrementing I. If I have come to I, which is incremented here, then I go back to the beginning of the loop, which is B. So from E, I go back to B. When I have this return false, then I directly jump to the exit, which is, so there are two dummy nodes being conceived here, just to make it easier in terms of the graph. So this is an enter node and an exit node, right? So this is my control flow graph. If I look at the linearly independent path, then I can see that one path is going like, I come here, I check this condition, it fails, and return true, right? So this red one, which is not going, this that is not going through this loop. The other paths could be which return false, or which goes through the loop and then returns true. I'm just semantically trying to tell you, and these are the paths that are shown here. So again, you have, though this graph is a little bit more complex than the earlier one, but you have 3 linearly independent paths here. Now, the question is, can you determine what is the number of linearly independent paths? How many linearly independent paths will be there? So there is a result, which is, there is a number for any control flow graph, or flow graph for that matter, which is called the cyclomatic complexity of the graph. So if G is the graph, then the cyclomatic complexity, or Vg, is defined by n e minus n plus 2. That is, n is the number of nodes in the graph, e is the number of edges in the graph. So if I count it here, I have 1, 2, 3, 4, 5, 6, and 7. 7 edges. So E is 7. I have 6 nodes. So that is 6. So 7 minus 6 plus 2 is the number of, is the cyclomatic complexity of this graph, right? So which is 3. Another way to get to this number is if you can find regions which are there in the graph and which are disjoint. Like there's one region is 1, 2, 3, 5, 1. This is one region. And 2, 4, 5, 3, 2. This is another region. Right? So you will not consider this bigger one as a region because it is, again, not disjoint from the earlier 2. So the total number of bounded areas, regions that you have, plus 1, will also give you the cyclomatic complexity. There are graph theoretic proofs for that. So, I'm sorry. So we will not get into those proofs. So here we have 2 bounded areas. So we have 2 plus 1, 3 as the cyclomatic complexity number. Now, the other result that is useful in this case is that the number of linearly independent paths of a program is upper bounded by the cyclomatic complexity, which is a very, very important result. So you can see that, well, depending on the cyclomatic complexity, I at least know that how many linearly independent paths, the maximum I can have. Right? We will see other use of cyclomatic complexity also. You'll see this is done by Maccabe. So this is known often as Maccabe's cyclomatic metric. This is a very typical metric. Like LOC, lines of code, is one metric. Number of functions is one metric. Similarly, this is a more explicit metric for the control flow in a particular function. So it provides a quantitative measure of testing difficulty and the ultimate reliability of the system. Now, the first method, which it takes the number of nodes and edges, is very simple that way. So you can easily write a program where from the graph, and you will know what is a cyclomatic complexity. Now, what does the cyclomatic complexity tell us? it in a way tells us a lower bound on the number of test cases to be designed, because I know from, as I stated earlier, that I will need, I may have, not necessarily, but I may have as many linearly independent paths as is the cyclomatic complexity of the graph, right? And obviously, I need at least one test case for checking a linearly independent path, right? At least one case is required. Now, obviously, the one test case would never be able to check two linearly independent paths, because it will go through at least through one path or through the other path, right? So which means that to check for the path coverage or check for the coverage of linearly independent paths, I need at least those many test cases. Now, Maccabe's cyclomatic complexity is an upper bound on that. So it becomes a lower bound on the number of test cases to be designed, which can guarantee that coverage of all linearly independent paths have happened. So that you can see that it gives a very concrete measure in terms of how difficult is it to test a particular control flow. So it does not obviously make it easier to derive the test cases, but it gives you, certain idea of the complicacy of the task that you have at hand. So now let us try to construct the actual path coverage. So we will draw the control flow graph. That is the first step. We'll determine the cyclomatic complexity Vg. Then we determine the set of linearly independent paths. Obviously, you might question that why am I computing Vg? That is often done to get an idea of how complex the whole task is. And once we have got the linearly independent path, then we need to prepare test cases to force execution along each path. Right? For example, here, if I have to do it, then I can see that if I have to force execution along the linearly independent path 1, 6, this condition must fail at the beginning. Right? So this condition will fail at the beginning if I negate the condition. Right? So if x is equal to y. So the test case which has x equal to y, for example, here I have taken 1, 1, is a test case for the linearly independent path 1, 6. Second is then I go into the other linearly independent path. So I have to make this case succeed. So in the remaining test cases, x and y would be unequal, will have to be unequal. So I get here, and then at 2, I have a choice. So either I have to take x greater than y, or I have to take x less than y. Obviously, x cannot be equal to y. So I make two choices, x greater than y, x2, y1, x less than y, x1, y2. And if I go through that, then I'll see that this path for x1, y2, x1, y2 will do 4. X1, y2, I think I have written this in a wrong order. If x is 1, y is 2, then this will happen. So it is 1, 2, 4. Then y becomes 1. So 5. Then I come back to 1. And then you go to 6. This need to be swapped. I'll correct. Right? But this is the basic idea. And it is not straightforward to automate this. It will need quite a bit. I mean, this was a simple program, so it looks kind of trivial, but this is a whole idea. And there are tools, obviously more expensive ones, which can help you construct these test cases. This kind of test generators will give you the linearly independent paths, and it then help you generate these test cases, at least tell you what kind of condition you need to put and so on. So cyclomatic number itself, or the cyclomatic complexity itself, kind of gives you an idea of the number of errors that could exist in the code, because that's a number of bound on the linearly independent paths. And it has been shown through several experiments that it indicates the psychological complexity of a program. Higher the psychometric complexity, it becomes more difficult for someone to understand that code. Right? This has been, and this is something which is very, very important. In the industry, very often you write very less new code. More often, you have to understand a code that others have written, and then analyze and possibly fix certain errors or write some small new inserted codes in that. So it is a good indicator of the difficulty level of understanding the program. So from the perspectives of maintenance, the cyclomatic complexity of modules need to be limited to some reasonable value. I mean, having a graph having a cyclomatic complexity of 100 would make it very, very difficult to some developer to understand or debug and do things. So many software organizations do use the cyclomatic complexity as a kind of design coding guideline, that they'll say that, well, restrict the cyclomatic complexity of every function that you write to a maximum of 10 or so, right? So as you do the code, you have to run the tool to find what is the cyclomatic complexity, and if it is more than that's bound, then you will have to think about a redesign to break it up in terms of semantically, of course, a number of smaller functions, right? So that's a whole notion of path coverage and cyclomatic complexity that comes out of the path coverage concept. So in terms of testing, if I may kind of summarize, then this is the hierarchy. Here the hierarchy is shown in the with reverse direction of arrows in terms of specialization. So at the base, you have the statement coverage, which is the simplest form, which can take you to condition coverage or branch coverage. And what you do more often is branch and condition, or condition and decision coverage together. Then you can do MCDC, that is modified condition and decision coverage. You can do multiple condition coverage, and separately you could do independent path or basis path coverage. I did not go into the details of that, but so all of these necessarily come down to the path coverage. So you can see that as we are progressing, it is more and more strong test strategies what we introduce, and obviously stronger the strategy, stronger would be more required would be the effort in terms of the test cases for that strategy, and the tools that apply that that strategy to measure the coverage along it. And there, but such kind of, I mean, what I showed you yesterday in LCOP was within this first part only, statement coverage and branch coverage, right? It had function coverage, which is not a very formal metric, but it's a very useful metric, right? So it gives you the measure. Okay, so this is kind of a summary of coverage testing approaches in white box. So let me go back and check before I proceed if there are questions that you have. Is there any question?
Sir, Java has reflection, so it is kind of easy or more feasible to do this coverage analysis. But in a compiled C++ program,
Mhm.
how are these things determined, especially the path coverage?
No, see, it is. I mean, I will have next week a specific lecture on different kinds of tools where I'll talk about those strategies. But most often, the tool that you use has to take the program as a source code. You cannot do this on compiled code. Right? So you so so instead of compiling with your usual compiler, you use the tools compiler, or tools embedding into your compiler, uh, and use a process known as instrumentation. For example, if you have to, just think of how you do statement coverage, right? Even in Java, it may have reflection, but how do you do statement coverage? Reflection is of no use in doing statement coverage. Statement coverage is necessarily a lexical concept, right? Statement is a lexical concept. So as you
You have the AST. You have to first have the AST into yourself and then inject something into
so
the
so so
bytecode
you'll have
to
to
recover.
do something, right? That the simplest way we can think of is I can put with every statement I could put a flag, right? And then so I have an array of flags, and I say, along with the code for the statement, I inject some code which sets that flag to true, indicating that the statement has been covered. Some tools actually have counters. So they not only give you the coverage data of statements, which is yes, no, but they will also tell you how many times this statement has been covered, how many times it has been executed. So you will get even a relative idea of the coverage. So what you need to do is, a whole basic idea is you take the source code and inject extra code into that. And that is the reason you need these all variety of tools. And of course that for some cases that creates a kind of problem, because if you do not have the source code, then most of these coverage tests you cannot do. You need to have the source code for this, but we'll
That's
talk
okay.
about
Without
some of.
source, what's the point for doing coverage anyway?
Yes, there is point. There is point. There is always a point. The point is, how reliable is that code, right?
Like,
you
if I'm not a developer, and I can't look at the source code, if I generate the coverage, then it's like audit only. You can't do anything with it.
you can decide to use a separate different library,
That's the thing.
right?
That's
So there is always a use, but there is always a technical feasibility of because this the how will it happen that you do not have the source code? It can happen when within your code you are using a number of other third-party libraries, including the standard library. Like, you do a coverage in your program. How do you get the coverage for printf? You cannot get the coverage for printf because you do not have that source, possibly, right? So what do you do? These tools allow you to mark functions which are like from third-party library, and you say you exclude them from the analysis. So all these kind of tool aspects are there. The engineering aspects are there. What we are now trying to look into is what could be the different set of strategies that can be applied at different levels of abstraction, so that we can get more and more detailed data in terms of how well I have tested my code. Right? Are you getting that idea, right?
yes, sir.
I'll talk about some tools for some tasks, at least, particularly in terms of fault coverage. I'll do that next week when I talk about tools which can actually work on the executable. Because one of the problems that happen with these coverage tools, which are source based only, most of them are, is that naturally, if you think a little bit more, for checking this coverage, you have actually instrumented the code, right? Which means you have injected
Yes.
some statements. Without that, you cannot do that, right? How do you know that if a function has been called or not? So
Hmm.
you have to inject some counter and so on. The moment you inject the code, your code,
Will
injected
follow
code
that's
used
the
for
same
coverage,
code.
might hide some error, right?
Yes.
For example, a very common type of error that we get is bounce failure, right? You have an
Hmm.
array and you have gone one position more than what your array was. It will mean that you are possibly corrupting some other variable which was allocated right after that array. But when you instrument, possibly after that array and before that other variable, you had that
Padding has been said.
instrumentation value. That instrumentation value got corrupted, but that gave you a wrong result which you did not understand. But when you do now, when you stop doing the instrumentation, when you do a production build, you do not have that cushion anymore. So it actually corrupts and gives you an error. So you see that on this test case, this was covered, the golden was achieved, but you do a production build, it fails. Right. So these are, even the production builds fail for several of your
Compiler optimizations.
optimization issues. Yes. So we will, I mean, when we do the compilers, you will see the real reasons of why such kind of things might still happen. But obviously, these tools are not the final answer to all your problems. But these tools really give you good handle in terms of what you can do and how you can expedite the whole process of development. Okay. Any
Yes,
other
sir.
question? Any other question? Okay, let us go back and continue again. So I'm back on slide 50. So in terms of white box coverage testing, this much is what we are doing now. Now I'll talk about two other testing methods in the white box, which are very useful but expensive. The first is known as mutation testing. So initially, you will test the software based on the white box strategies that we have already discussed. But after the initial testing, you could take up mutation testing. Mutation testing is like it has different purposes, but the most significant purpose is to ensure that your test suite that you have, that is a set of test cases that you have designed based on this black box information, black box strategy, and the coverage strategy, how complete is that test suite? Is it really a good one? Is it really catching everything, and so on? So how do you do that? So what you do is what is very common in hardware design is you inject a fault. So you make a few arbitrary small changes to a program at a time. Do not do a lot of changes, because then the whole behavior becomes different. But at selected points, you make a change, inject a bug. If your test suite is complete, then you will be able to detect that bug by running the tests. So you inject a bug, you run your test suite and see whether you are getting an error. Now, the change that you inject is known as a mutant, because you are mutating the code. So if after injecting that mutant, if your test suite passes without failure, then your mutant remains alive. Then it's an alive mutant. That is a bug which your test suite will not catch. So you go back and check on the test suite. You need to add more tests. If the test suite gives you an error, at least one test case fails, then that mutant has got killed. It is called a dead mutant, because that bug is no more something that you may be concerned with, because you will always be able to catch that with that test case. Right? So, like very pathological examples we can see here. For example, here we are looking at a small code which reads a value x and checks if it is 0, then increments, otherwise just proceeds. So the question is, in terms of statement coverage, what will cover this code? In terms of statement coverage, if I have x as 0, then this will have 100% test statement coverage. This is read, x is 0, so this condition is checked, it is true, so 3 is executed, 4 is executed. So it has 100% test statement coverage on 0. but it does not have 100% branch coverage, because at x equal to 0, one branch is true, which brings it to 3. 2 to 3 branch you have tested through x being 0, but 2 to 4, that branch has not got tested. So very concrete example of, I was possibly just stating it earlier, very concrete example of why test statement coverage may not give you 100% branch coverage, right? So you will need to add another test case. So now if you have x0, y1, x0, x1, two test cases, then you'll have 100% branch coverage, and obviously that will have 100% statement coverage. Now suppose you have a code like this. Right. Why will you have that is a different question. What I'm representing as true may not be written as true. And if it's written as true, then it is quite, obvious. The compiler itself will say that, well, this is that what you wanted to do, because then this condition check is not actually required. Now, if you have written, but it could be a complex condition which eventually becomes a tautology, which very often happens. Now, how do you check the branch from 1 to 3? You cannot do that, right? Because no matter what kind of test cases you write, this tautology will remain a tautology. Right? So this is where you can use, this is a place where you can use mutation testing. That you see that, no way this branch is 1, 3 is getting covered. So let us force a value so that 1, 3 happens, and then see what is that is going to take the shape. So these are the different reasons you do mutation testing. I talked about all this. So the whole process is of mutation testing is to design smartly design mutants, create the mutated program, run your existing test suite to try to kill that mutant. If you can kill, if the mutant gets killed, then you stay with that, create a new mutant. If it does not get killed, then you go back to your test suite and design more test cases. Right? So these are some of the typical, mutation that people do, or the tools allow you easily to do. You can delete a statement, you can alternate an arithmetic operator, you can change the value of a constant, change the data type, and so on. So several things that the tools allow you to do. So obviously this is more expensive to do. Because it is not possible for an automated tool to tell you what should be the mutant. It can tell you about the coverages, it can tell you about what is not covered, you can go and check. For example, a very necessary way to requirement of doing mutation testing comes to test for your exception paths. Because often maybe there are input conditions which you can conceive might arise, but you have no way of simulating them. So what you do, you go to the code, inject that, okay, that has happened. So is my exceptions taking care of it, and so on. Right? So that is about the mutation testing. The other, which is very, very useful, and you will actually learn a lot about this approach in your compiler course. This is just kind of uses the basic results from that. So I'll be a little bit on the surface on this, because it needs some bit more detailed understanding of the compiler and the abstract syntax tree and so on. So it is called a data flow testing. It's a type of a structural testing yet. It is used to find test paths of a program according to the definition and use of variables. Right. So it is concerned with two kinds of statements. One are statements where variables get their values, they get defined. And the other kind of statements where variables are used or referenced. So if I have a statement numbered as S, then I define two sets for S. One is def S. Def S is a set of variables that contain a definition of X. And use S is a set of variables that are used at statement S. So if I have A assigned B as my statement 1, then def 1 is A and def and use 1 is B. A is being defined and B is being used. For example, here in statement 2, I have A assigned A plus B. So def 2 is A, it is being defined. Use 2 is A and B both, because both are being used. So if a statement is a loop or if condition, then def set will be empty and the use set will be based on the condition of the statement. So we talk about you know condition use or predicate use in terms of the variables. Now, why is this important? Because this can tell you about a lot of possible faults. For example, a variable may be defined but not used or referenced anywhere. Right. The question obviously is one is it may be redundant, unnecessarily holding on to memory. But a deeper question may be that somewhere you may have just mistyped, and instead of this variable, you have used another variable. So more critical is a variable is used but never defined. You started using it with a garbage value, unless that is intentional. I mean, there are cases like, for example, random number generators, which try to use the garbage value that exists at one or more variable locations as seed points. Many generators do that. So unless you have that kind of a special program, it is obviously meaningless to use a variable without defining it. Or a variable is defined twice before it is used. Obviously, the first definition will get erased. Then why does it exist? So this kind of. So you find out this kind of information by data flow based testing. So advantages are obvious. It is to find a variable that is used but never defined, defined not used, defined multiple times, deallocating a variable before it is used, and so on. Naturally, the disadvantage is it is often quite intense in terms of the analysis that you need to do to get to this these kind of information. It's a time-consuming and costly process. And obviously, it requires a knowledge of the programming language itself. So let us look at simple examples. So say you have read xy. If x greater than y, you're assigning x plus 1 to a. Otherwise, y minus 1 to a. Then you're printing a. So this is the control flow graph. 1. Then you have 2, 3, and 4 branched, merged at 5 is a simple control flow graph, which you will actually require to know if different conditions exist. So here, if I have to use this graph, and there is a detailed set of algorithms to find these kind of quantities on the control flow graph. These are they form a set of recursive definition and then solves them to find the answer for this. So this is called come under the broad topic of data flow analysis, DFA, and is a part of the compiler design course. So then you will get to know how to find this, but here we are just doing by observation. So it's a variable x is you have a read. So it is defined at node 1. It is used in 2 and in 3. The uses are different. You can see that this is kind of a use in predicate. This is used in an arithmetic expression. So 2 and 3 are the use nodes. Y is defined again in 1 and used in the condition check 2 and in the assignment 4. A is defined in statement 3 as well as in statement 4 and used in the printing 5, right? So naturally, You can see that if I can build this information, and there could be this is just isolated information. It is X is defined here, used at 2 and 3. But after that, there could be another definition of X. X could be assigned another value or read another value and so on. So there could be another definition. There could be subsequent uses of that. So it is just not that a set of define and use, but it is define, use, define, use, define, use. So this is kind of as the variable goes through its life cycle through the program, we have what is known as DU chain, definition use chain. So this is like becoming like a chain. So every use must have a unique definition that reaches that point, right? Only then that is a meaningful thing. So if you have this DU chain, then you can very easily answer many of these questions. For example, I can say that let's say defined before use. If I'm trying to find out, is a variable defined before use. What I can do, I can have a dummy node 0 here before this 0, right? And a node at which I assume that all variables are defined. Those are garbage definitions because that's what is happening at the time of memory allocation, loading of the program. So I have a dummy node 0 here. Now I build the DU chain for every variable. So what will happen after that dummy node here, I will have a read XY. So the definition that will reach node 2 or node 3 is the definition at node 1, not at node 0. Right? But if I did not have this read XY, then what will happen? X will be defined at node 0, Y will be defined at node 0. So I can just extend this algorithm by this small amount and then check that in the DU chain, do I have a definition that is at statement 0? If I still have with some use, then I will know that, well, it is used before being defined. If I have an empty use set in the DU chain for a definition, before I have the second part of the DU chain, that is the next definition, if I have an empty use set, I know that it is a case of a double definition. Very easy to logic, right? If I have one segment only in the DU chain and I have a define and I do not have any use, then I have the case of defined but not used, and so on. Right? This is called unreferenced variable. So data flow, I mean, what you need for the data flow testing, quite a bit of that actually is already a part of our compilers. So if you carefully, that's one of the reasons, again, I reiterate that you must look at the warnings carefully, not only the errors. Errors are showstoppers, they cannot allow you to proceed, but you must check each and every compiler warning and make sure that you remove that warning. Yeah. So you will often get this kind of information, particularly not the double definition, but you will get used before defined. You will get a warning from the compiler. The compiler will tell you that no, you are using a value which is not defined. Are you sure you want to do that? Or you will also get information about defined but not used. So we'll say that unreferenced variable. Right? So these are kind of other types of tools, types of analysis that white boxing involves with. So there are more detailed analysis that are possible. I'm not. I did not include those details. You'll wait till the compiler course to learn about them. That you can have a particular object in different categories, a variable in different categories. It may have been defined, it may have been created, it may have been initialized. Similarly, it could have been killed, it could have been undefined, it could have been released. It is used in a calculation like arithmetic expression, or it is used in a predicate. So all these different kind of things you can actually find from this data flow testing approach, from the data flow analysis tools. This example in a little different way, it shows you all classified use of calculation use and the predicate use. Z and Y have predicate use, and these have calculation use and so on. Okay, so let us, so that was up to the black box and white box testing approaches. There are some more techniques, but we will kind of stop here. This is comprehensive enough for doing any kind of testing. Before I proceed further on different other aspects of testing, like debugging and how to really build up your test environment and what are the test tools and so on, let me spend a little bit of time on the test plans. What is test plan? I mean, you all have by now, by practice, have started understanding test plans, but let me a little bit more formalize it and show you three different examples to show what are the kind of things that a test plan might expect. Now, before I get into the test plan, let me define positive and negative test cases. When we we have typically positive and negative. Is it time? Oh, I'm sorry. I'm sorry. It's time, right? Hello?
Yes, sir. It's 9:05 already.
Oh, you should have told me. Anyway, okay, I'm very sorry. I will stop here. The test plan and remaining we will do in the next class. And up to white box testing is what will be included in the quiz in the next week, which is on 31st. Right, as you know, with the laboratory, we'll have this theory quiz also. So we'll have SDLC, UML, and this initial part of the testing as a syllabus for the quiz. Thank you very much. I'm very sorry. I just didn't look at the watch. I was engrossed in talking. Thank you. See you next week. Have a nice weekend.